Welcome to Black Hat. You are currently in the upper layers track. We're here to hear about the Google Native Client from Chris Rolfe.
Thank you. Thank you. Okay, so obviously the title of my talk is Google Native Client, analysis of a secure browser plugin sandbox. If you can't tell, I tried to fit as many possible buzzwords into that title as I could. Just a little bit about me. My name is Chris Rolfe. I'm the founder of Leaf Security Research. I'm a Black Hat Review Board member and past speaker. I spoke here in 2009 and then again last year. Always love speaking here. It's a really good crowd, really good attendees. You can find me on Twitter. My Twitter handle is just Chris Rolfe. My email address is chris.rolfe@gmail.com. And my website, feel free to contact me after the talk if you have questions or you just want to say hi. Before founding Leaf SR, I worked for Matasana Security in New York. Before that, I did some other enterprise security stuff, and before that, I worked for DoD for a little bit. So just some background on me. A few words on why I decided to look at Google Native Client. It's pretty obvious that browsers are the new platform for applications. This has been true for a long time. Mostly because of portability, right? No matter what operating system you run, you have a browser. They all use the same standard protocols, HTTP. So really, it's a standardization thing. So a lot of new applications are being pushed, whether in web app form or plugins or whatever. This is definitely true and will be true going forward. Secondly, sandboxes are definitely the future of application security. I'm pretty certain that within 5 years' time, every new major thick client that's released, whether it be browser or otherwise, one of the first security questions that we're going to be asking is, what does its sandbox model look like? What does the broker process look like? You know, how does it handle privileges and handling tasks from unprivileged processes? So sandboxes were something I was really interested in, and Google Native Client brings some new things to the table in terms of sandbox technology. And I'm going to obviously talk about all of that today. And of course, last, breaking easy targets is really boring, right? Like we can all just throw long strings of A's with some fuzzer at some target that no one's actually looked at before, but that's just boring because you know it's going to fall over. With Native Client, it was really a challenge for me because it's written by very smart people, and it was designed to be secure from the ground up, right? It actually is a security technology. It's a sandbox, and right now sandboxes are as tough as it gets as far as countermeasures and defenses. So from the very beginning of Google Native Client, it intrigued me to try and find vulnerabilities to break out of the inner sandbox or find ways that they didn't anticipate sandboxing untrusted code. So for those of you who aren't actually familiar with Google Native Client, I'll kind of give you a quick rundown. I'm sure everyone here in this room has run a browser plugin at some point. Usually it's an NPAPI plugin or it's an ActiveX plugin in Internet Explorer. And the problem with those two technologies is that they put security in the hands of users, right? You get a pop-up that says, do you want to run this browser plugin? And you're basically asking the user to decide whether a plugin is malicious or not, right? And that's just ridiculous. And we've all sort of suffered the consequences of that since its inception. Google Native Client takes a different approach, and it says all plugins are malicious. We're going to treat every single one of them as malicious. They're all going to live in a sandbox regardless of where they come from, and we're going to vet each one of them before we load them. It takes a much different approach than NPAPI or ActiveX. In the case of those two technologies, your browser plugins have complete access to whatever your browser has access to. There was this misconception a while ago that NPAPI was more secure than ActiveX. It's kind of a joke. There's actually some more things you can do with ActiveX to lock it down than NPAPI. But at the end of the day, if you allow the plugin to run, it has complete access to your machine and your system. And that's ridiculous. Like why should just some game you pull off the internet have access to your entire hard drive, right? It shouldn't be that way. That plugin should be sandboxed, and that's what Native Client tries to do. A lot of security people don't even know that Native Client is now in Chrome by default since version 14. But there are some restrictions there. You can only load Native Client modules that were downloaded from the Chrome Web Store. You can't just download them from anywhere. And while that's the case today, that's not always going to be the case. The architecture behind Native Client is really, really complex and large, and I'm going to talk about each one of these individual components today. But just a quick rundown. There's a modified compiler toolchain to produce them. You can't just use GCC, you can't just use LLVMs, Clang to produce Nexi modules. And Nexi modules are untrusted Native Client plugins. So you need to use the plugin, you need to use the compiler that comes with the SDK. There's a secure ELF loader for actually loading Nexi modules into memory. It doesn't use the regular loader that's found in your operating system kernel. There's a disassembler and code validator. If anyone here has written a disassembler for any architecture, you know how difficult that is. There's a service runtime that sort of facilitates the Native Client module at runtime and handling requests that it makes. There's the inner and outer sandbox, and this is two really important ones that I want to talk about. When I say outer sandbox, I mean the sandbox provided by Chrome. And even though the outer sandbox plays a pretty vital role in keeping Native Client modules, Nexi modules contained, it's sort of out of scope for this talk. So anytime I say outer sandbox, just assume that, just know that I'm talking about the sandbox that's provided by Chrome today. When I say inner sandbox, I'm talking about the second sandbox that's actually provided by Native Client. Then there's SRPC and IMC, which are two different protocols that Native Client uses to move data back and forth between the untrusted modules and the Chrome browser. And then there's PPAPI, which is also known as Pepper, which is the actual plugin implementation found in the Chrome browser. And again, I'm going to talk about each one of these components, but just to give you a snapshot of how large and complex the Native Client architecture is. And I'm going to try and go through these in a logical fashion, but I kind of have to jump around just by the very nature of the software. I have this diagram, and I'm going to have this architecture diagram, and I'm going to bring it up before each section, right? Because I don't expect anyone to remember what this looks like, because it's pretty large. But up here in the top right, you have the sandbox renderer process, right? This is where WebKit lives. This is where the V8 JavaScript engine lives. This is where the Pepper implementation lives. And then down the bottom left, you have the sandbox secure loader service runtime. That's where the untrusted Nexi modules live. And then in the top left, you have the Chrome broker process, which is like the sort of more privileged process that handles privileged requests from unprivileged components. So again, I'm going to keep bringing this up, and every time I bring it up, the section I'm going to be talking about is going to be highlighted in red, so to make it a little less confusing. Another very important point is levels of trust, right? It really depends on what context we're talking about. When we're talking from the outer sandbox, when we're inside the outer sandbox, the Chrome broker is the only trusted component. The Chrome renderer process is not a trusted component. It's untrusted. The NACL service runtime is considered untrusted. The Nexi modules are certainly considered untrusted because they come from arbitrary sources, or will in the future. When we're talking in the context of the inner sandbox, the Chrome broker, of course, is still trusted, but now the Chrome renderer process is also considered trusted. The NACL service runtime is now considered trusted, and the untrusted Nexi modules are, of course, still untrusted. So just to kind of put this into context and make it a little bit more sense, if you're able to go from an untrusted Nexi module into the Chrome renderer process, you've actually completed a privilege escalation because you've left the inner sandbox and now you're in the outer sandbox. So that's why we consider the Chrome renderer process trusted when we're talking in the context of the inner sandbox. I know that gets a little confusing, but just remember, obviously, the inner sandbox is within the outer sandbox. Okay, so I'm just going to jump right into the architecture. The Pepper API, which also is PPAPI, those two terms are interchangeable. And that lives up here in the top right, Chrome renderer process, which of course lives in the outer sandbox. And it lives alongside WebKit, which handles HTML parsing. It lives alongside the V8 JavaScript engine. So Pepper replaces NPAPI. NPAPI still exists in Chrome, but NPAPI was designed for browsers that were written 10 years ago, essentially. I don't know about any of you, but my browser looks nothing like it did 10 years ago. It's entirely different. So NPAPI is kind of aging, and I think Google took the initiative to come up with this new standard called Pepper. So there's new APIs for things like audio and 3D and input devices, and there's privileged interfaces for things like file I/O. And in a properly sandboxed web browser, a privileged interface like file I/O wouldn't be handled by the browser itself, right? It'd be passed off to a privileged component like the Chrome broker process to go and then open that file and then send things over some channel. Another one of the major differences between Pepper and NPAPI is that Pepper is no longer scriptable via JavaScript the way NPAPI was. If anyone here is familiar with NPAPI, or if you've ever written a plugin or scripted it, there was this thing called NP runtime, and you could bind JavaScript calls to NPAPI C++ calls, and essentially just call them from any website. That's gone now. So there's no more NP runtime in PPAPI. They're not scriptable the same way. And that makes that's kind of a big difference between the two. Kind of reduces a lot of the attack surface that existed on NPAPI plugins. Another thing that's a big difference between Pepper and NPAPI is that out-of-process plugins are now supported by default. This was something that NPAPI kind of strapped on a few years later because you had browsers and they had plugins like Flash, for example, and when Flash would crash, the browser would go down with it. And I think browser makers, were like, well, that's not really, we can't do anything about it. It's not our code. So we'll just kind of bolt on this out-of-process NPAPI thing. And now the plugins, when they crash, they're out of process, so it doesn't matter. So now Pepper supports that just by default, by the standard. So when we talk Pepper plugins, there's trusted Pepper plugins and there's untrusted Pepper plugins. Trusted Pepper plugins live inside this, the Chrome renderer process, or they live inside another Chrome process that's equally as sandboxed. Two good examples of this is the Native Client plugin itself is a Pepper plugin that lives within the Chrome renderer process. And a good example of an out-of-process Pepper plugin is the Adobe Pepper Flash, which was just released, I think just a few weeks ago. And that sort of just talks to Chrome over Chrome's IPC layer, but lives out of process, but within the outer sandbox, of course. Untrusted Pepper plugins are native client modules, or known as Nexi modules. And they communicate with the Chrome renderer process and the Pepper implementation using a proxy. And I'm going to talk about that proxy a little bit, because that's one of the really important points when we talk about native client attack surface. So this brings us to the actual native client plugin itself, right? I'm trying to stack these components architecturally, but logically. So we have the Pepper implementation, and the native client plugin is a Pepper plugin. So it sort of builds on top of the Pepper implementation itself. And the native client plugin lives up here in the right-hand side with the sandboxed renderer process, again, alongside WebKit and V8 and the Pepper implementation itself. So it's in process. It's just a regular DLL. There's nothing special about it, right? It just gets loaded in like any other DLL and works like any other Pepper plugin would, almost like any other NPAPI plugin would, right? It's just a regular DLL that's compiled and sucked in by the Chrome browser. And you can invoke it via this HTML tag. So we have this HTML embed tag, and we have regular parameters here, stuff we're all used to, like name, ID, width, and then we have source. And if you look at source equals here, you'll see hello world.nmf. NMF stands for NACL manifest file. And what the NACL manifest file is basically describing to the Chrome browser what components are required for this native client module to run and where they can be found. And it's just basically a few lines of JSON. You can see here, I kind of condensed it for the slide. But you see files is like this, one of the object names to begin with, and then you see libgcc _s.so.1. That's one of the shared objects that this Nexi module needs to run. And then there's the architecture it was compiled for, x86 32-bit. And then there's the URL that you can find that shared object at. And again, you just go down the list, there's main.nexi, and then some other shared objects that it needs to run. And this the native client plugin parses this JSON with a third-party library called JSON CPP within the Chrome renderer process. It's actually really simple. There's not much to this. You can't really describe too much of the native client module other than what you need to run. So it's one of the smaller parts of the trusted code base. So what's going to happen now is the native client plugin is going to look at those URLs and it's going to see where that Nexi module can be downloaded from. And it's going to use the Pepper interfaces to go and download it. And it's going to use URL loader and the file IO interfaces. What it's going to do is say, hey Pepper, here's this plugin. I need you to go download it for me and either put it on the disk or put it in this memory buffer and give me a handle to the memory buffer. And I'll go and do whatever I want with it. So the native client plugin obviously has to expose itself to the DOM a little bit in order to be instantiated and controlled from JavaScript and sort of alert the user to what's going on. But obviously I just mentioned a few minutes ago that it's not really scriptable anymore the way NPAPI plugins are. So this surface has been like greatly reduced. You basically just have a few properties with basic getters and setters. There's 3 here: ready state, last error, and exit status. It's basically just for informing the user via JavaScript whether a native client module loaded or crashed, or what status it is at that time. And then you have this function called post message. Post message is sort of the most important part of how PPAPI plugins communicate with JavaScript. Post message basically just takes an opaque blob of data and sends it down. So for a Nexi module to be able to talk to JavaScript, it needs to implement a few interfaces. One of those interfaces is PP instance handle message, and it needs that to be able to receive messages from JavaScript. And then, of course, it wants to send messages to JavaScript. It has to implement this interface, PPB messaging post message. And in JavaScript, the way this works is you basically just set an event handler on your post message handle. And anytime data gets received on that interface, it's just going to call one of your JavaScript functions that you supplied it when you set up that event callback. And you're going to have some data. And again, the cool thing about post message is that there's no format to that data. If you can make it binary, you can make it ASCII, it can look like whatever you want. It's up to the application developer to sort of define what those structures look like. So there's no more saying, hey, my plugin has these 5 methods, and if you want to do these 5 things, you call these 5 methods. So we just sort of like change we change the way that looks, right? So now it all goes through post message, and it's up to you on the back end to sort of decide what that looks like. So now that the native client module, now the native client plugin has a native client module downloaded, a Nexi downloaded, it has to ask the broker process to start the service runtime. In the service runtime, and I'm going to talk about this a little bit, but what the service runtime does is sort of encapsulates the untrusted Nexi module and makes sure that it can't escape. So once the service runtime process has been started by the Chrome broker process, the native client plugin and the Chrome broker process, and the Chrome service runtime process are going to establish an administrative SRPC channel. And basically this channel is used to say, this is the Nexi module I want you to load, these are the SRPC channels I want you to set up. So once that's set up, there's going to be some individual SRPC channels set up between the untrusted Nexi module and the native client plugin. And that's where it kind of gets interesting, right? Because the untrusted Nexi module can talk over those interfaces. Oh, and I should also mention that the service runtime that gets started by the broker process also lives within the Chrome outer sandbox. So I mentioned the Pepper proxy, right? That's how the untrusted Nexi modules actually communicate with trusted components so that can actually do useful things. And the Pepper proxy is actually implemented by native client up here in the top right sandboxed renderer process. And again, it lives alongside V8 and WebKit and PPAPI. This is sort of one of the main things that the native client plugin implements that makes it necessary. So if a native client module, a Nexi module, is completely sandboxed and it can't do anything useful, then what use is it to a user? How can they actually use it to do anything? Well, it needs to be able to talk to privileged interfaces, and those privileged interfaces all live in the Chrome browser itself. So we need to facilitate communication between untrusted Nexi modules that live in one process and privileged components like PPAPI that live in another process. So the Pepper proxy is the bridge that sort of implements that. And it's really, really important to the attack surface of native client because that's where all the untrusted data that you can't vet beforehand because it came down from a website, that's where all the untrusted data is going to go over and be received by trusted components. So the Pepper proxy has these web IDL files, and IDL stands for Interface Description Language. And those files basically just describe the interfaces, the arguments those interfaces take, the return values that they return. And a lot of the Pepper code is actually just auto-generated with Python scripts that suck in these IDL files and just produce C++ code. And to make things more confusing, both sides of the Pepper proxy, both the untrusted side and the trusted side, can both act as both client and server. So there's a lot of shared code between those two components. On one side, the untrusted side, it doesn't really matter so much because you're executing code in a place that you can already execute code. But obviously we're interested in interfaces that are implemented on the trusted side, the area we want to start executing code in. If you're ever brave enough to actually check out the native client source code, and I encourage you to, there's a simple rule to help you differentiate between the different interfaces, because it's all in one place, because a lot of the code is shared. So any interfaces that are prefixed with PPP are on the untrusted side, right? PPP is, that last P stands for plugin, right? So it's all implemented on the untrusted Nexi side. All interfaces that are prefixed with PPB are implemented on the trusted browser side. Obviously, B standing for browser. So the Pepper proxy protocol stack is kind of interesting. And because I'm terrible at explaining this, I made a pretty picture. So up top there, we have the trusted Chrome renderer, and the native client plugin lives inside of it. The native client plugin implements the Pepper proxy, and then of course the Pepper proxy talks over the SRPC and IMC protocols. And I'm going to get into those, but those sort of just go down through the operating system and come back up the untrusted side of the stack, through IMC, through SRPC, through the Pepper proxy on the untrusted side, and then finally through the service runtime and the untrusted Nexi module. And the data that gets pushed over those is serialized as this data structure called ppvar. ppvar is really, really simple. It's basically just two very simple structures. You have ppvar type, which is just like a C enum that specifies the type of ppvar, right? The basic value. I'm sorry, the basic type. And then you have ppvar value, which is a union, and that union contains like an integer, a char, a double, or a bool, and a bool. And then you just package those two up as a ppvar structure. And you can, lots of different interfaces take one of these structures, they take two of these structures as arguments. It just depends on the interface. So those get serialized up by SRPC automatically and sent over the wire. I should say sent over the operating system because it's all local. I know no one can read this because I can't even read this. But I've made a graphic here, so if you download the slides later, this will be helpful, I promise. But essentially, this is an end-to-end call of how an untrusted Nexi module makes a call through the Pepper proxy up through the trusted side. I can actually read this better on that screen. So you have the untrusted Nexi module down the bottom, and you call get browser interface, and you pass it this constant ppb. Again, that interface is implemented on the trusted side. Graphics 2D interface, right? So you want to call some method on the remote graphics 2D interface. You have iFace, which is the variable we assigned it to, and then we call create, and we just pass it some data. Thank you. Cool. And that's going to go over this trampoline springboard. This is area code here, and I'm going to explain that in a little bit. Goes down through a native client syscall, and now here we're in the trusted service runtime. And then again, now we go out over SRPC and IMC through the operating system, up through the trusted side of the Chrome renderer process, where it's received by this function here, ppb graphics 2D create dispatcher. This is one of the functions that's auto-generated via those IDL files. Right? They're really, really simple functions. They just say, this is the interface, these are the arguments it takes, these are the argument types, this is return value. You can really easily generate code for that and then pass it off to the proper implementation. And then it goes down here through deserialize 2, where we deserialize that ppvar. As you can imagine, that's a ripe area for vulnerabilities. And then down here through this PPAPI thunk, which decides what PPAPI interface am I going to pass this off to actually have whatever the native client module requested done. And then up here through PPAPI itself. I promise, if you ever look at native client source code, you will come back to this graphic. It means nothing now, but I promise you will come back to it. The Pepper proxy is also responsible for being sort of this glue layer between SRPC, right, this low-level protocol, and the actual Pepper implementation itself. So you have a scenario, let's say you have a scenario where you have an untrusted Nexi module, and it wants to, let's say, use audio, for example. It wants to fill up an audio buffer with raw audio bits. Well, that could take a while. So it calls this interface, this audio interface, and it says, hey, here's this buffer, fill it up with audio data. I know it's going to take you a while, so whenever you're done, just call this callback. And then it returns. Well, obviously, we have to track some data when that happens. We have to remember what SRPC channel that call came in on, so that when we're finished, when PPAPI is finished, crunching the numbers for that audio, it can then call the untrusted Nexi module on that SRPC channel. So you can imagine there can be some confusion here, and I did find some vulnerabilities here I'll talk about towards the end. But a few things about callbacks. They're always bound to one specific SRPC channel. If there ever is confusion there, it's a terrible vulnerability. And of course, callbacks can only be invoked on the main thread, and the main thread being the main thread in the untrusted Nexi module. And the reason for that is, again, you could have confusion where one thread sets a callback and another thread receives it, and that could certainly be an area of vulnerability. One thing to note is that the Pepper proxy is absolutely not a security boundary. It does very little validation of data whatsoever. There's a few instances where it'll check like length values of some buffer, but in the end, it doesn't really know anything about the data. It just knows that it has some data, it has to pass it off to a specified interface, and it has to deserialize that data. So all it is a go-between untrusted Nexi modules and the trusted PPAPI implementation. Okay, so this is sort of the, I guess, interesting part of the talk. The actual native client bits itself. Not so much the native client plugin Chrome side, but the actual service runtime side, where the untrusted Nexi modules run. The native client toolchain doesn't necessarily belong in this graphic, but I felt that I would add it here. The NACL toolchain produces the untrusted Nexi modules that are going to live down here in the bottom left in this service runtime process. And again, like I said in the beginning, you have to use the native client SDK in order to produce untrusted Nexi modules. You can't use GCC, you can't use LLVM. And the NACL SDK ships with a modified GCC toolchain for producing native client models exactly to their exact specifications. And the current SDK can produce Nexi modules for 32-bit x86 and x86 64. ARM is coming, and I have a slide for that sort of at the end, but in the current SDK, it can only produce Nexi modules for these two architectures. Every Nexi module is compiled and linked as an ELF. And ELF stands for executable linkable format. If you're familiar with ELF at all the familiar typical structures that you see in an ELF binary are there. The ELF header, the program headers, the dynamic segment, all the relocation entries, symbols, it's all there. It looks like a regular ELF module. Google was really smart when they did this, in my opinion. They could have produced a proprietary bytecode and had some machine, virtual machine like Dalvik or something like that, but they chose to just to create native client modules as ELFs. And because of that, you can use all your standard tools on Nexi modules. You can use readelf, which is found in every single Linux distribution. You can find, you can use IDA Pro to disassemble any Nexi modules. All those standard tools just work right out of the box. The NACL toolchain, why do you have to use the NACL toolchain? One of the most important reasons is that there's a few blacklisted, I shouldn't say a few, there's a lot of blacklisted instructions that just are not allowed to exist in native client modules. They'll be thrown out at runtime, so they'll never be emitted by the SDK. That's sort of required by the inner sandbox. And then the other big one is actually how code looks in the untrusted Nexi module. All code has to be aligned to 32 bytes. And I have some assembler code up here you can kind of see. If you look at the very first address here, hex 1000 AC0 is 32 byte aligned, right? So that's the start of this function. And if we look down like 6 instructions, we see two branches. One's a conditional branch, and one is a branch that will always be taken. And then after that, you see some NOPs. And those NOPs will continue until the next 32 byte aligned chunk of code. So this is how we change execution. This is how we move between functions. It always has to be 32 byte aligned, and we're always going to use a branch instruction or a call instruction that can be vetted. And I'll talk about how they're vetted in a minute. Of course, no instructions may straddle that 32 byte boundary. If they do, that would mean you could hide instructions within that boundary, and that would be terrible. That would allow you to escape the inner sandbox, because on x86, you can jump into the middle of an instruction and start executing code. So a good example of a blacklisted instruction and why it's blacklisted is actually the return instruction. There's no return instructions in native client modules. And the reason for that is you can imagine a scenario where you have two Nexi threads, and one is busy doing something in a function, and the other Nexi thread decides to, on purpose, trash the stack of the first thread. When the first thread is done doing whatever it was doing, it's going to pop its return address off the stack and return to it. Well, that return address could be into the middle of another instruction, and that's not allowed in native client. Every instruction that will ever be executed by a native client module will actually be validated by the service runtime validator. And I'll talk about how that's actually done in a minute here. But if obviously we need to change states between functions, that's manually done, right? So we're just using jumps and pushes and pops as opposed to return. So branch instructions always have to be properly aligned to validated code. So if you have a jump to an absolute address, the service runtime is going to make sure that that address is always 32-byte aligned. And the NACL toolchain will make sure that any jumps that are ever emitted into a NEXI binary will always land in a 32-byte aligned address. And this sort of prevents attacks where you have a vulnerable NEXI module and you overwrite some function pointer. Normally you'd be able to take control of that, through maybe like a use after free vulnerability where you take control of a function pointer and then you call that register that overwritten value lives in. So if you look down the bottom, I have some more assembler. We have a register EAX. At runtime we don't know what's in EAX. It could be anything. In this case, it's 10057A hex. We're going to do a logical AND there and just make sure that it's 32-byte aligned by using this constant. So no matter what value is in EAX at runtime, we know that it's 32-byte aligned. And we know that this module wouldn't even be running right now if we hadn't validated all the code that started at 32-byte aligned chunks. So the NACL toolchain, in summary, is sort of responsible for ensuring that all the ELF structures in the NEXI binary are properly formatted and they all look sane and only safe instructions are emitted. It's going to also make sure that all branch instructions are properly aligned. Otherwise, they'll be thrown out at runtime when the service runtime goes to execute the binary. But obviously, an attacker can always modify a NEXI binary after the SDK has produced it, right? So that's where the service runtime comes in. And the service runtime lives down here in the bottom left in the sandbox service runtime process. You can see above service runtime it says trusted. And then below that it says springboard and then trampoline and then untrusted in NEXI. That's because they all live in the same process. The untrusted NEXI module lives in the same process as the trusted service runtime. And that's really the only way to enforce the inner sandbox. And just to reiterate what I said earlier, the service runtime is a standalone process that's launched by the Chrome broker once the native client plugin has downloaded a NEXI module. They share a virtual address space. The service runtime memory is trusted. The NEXI module memory is untrusted. The separation between those two components is the inner sandbox. And the only way to enforce the inner sandbox is have them both in the same virtual address space. Okay. So the ELF loader actually also lives in the service runtime, right? Native client's not going to use the ELF loader that lives in your operating system, say if you're using Linux or something like that. It has its own ELF loader. And what it's going to do is go through each one of the ELF segments found in the NEXI binary, and it's going to make sure that all of those things found in the various ELF structures look sane. It's going to make sure that all the length values match up, all the count values of how many structures are found within this segment match up. It's going to enforce that there's only one executable segment. You can only have one, right? And it's going to enforce that the .text lives within that segment. It's going to make sure that all load addresses look sane, that you're not trying to load something where it shouldn't be loaded, because native client will sort of force you to one area of memory so that it can make room for the trusted code. The instruction validator also lives in the service runtime. And what the instruction validator does is make sure that no one fiddled with the NEXI binary after the SDK produced it. Again, if the SDK can always produce instructions that are 32-byte aligned, but an attacker can mess with that after the fact. So what it's going to do is it's going to take the trusted entry point out of the ELF header, and it's going to start disassembly and instruction validation from that address, right? That's a trusted address. And it's going to exit, of course, on any blacklisted instruction. Blacklisted instructions include things that are going to modify the segment registers on 32-bit Intel, because those are sort of very important for the inner sandbox design. It's going to exit on things like sysenter. Native client modules can't make direct syscalls on their own. They have to go through the service runtime. Various prefix bytes on branch instructions that would allow it to sort of ignore the segment registers and jump into trusted memory. It only performs static analysis on the code, right? It doesn't do any runtime validation of the code. It assumes that after its static analysis, everything is good to go, and that the module conforms to the rules that the native client service runtime requires. Again, I had this example before, but I bring it up again now because now we're in runtime. We're about to run this binary. Again, we don't know what's in EAX, but it doesn't matter because we're going to do this AND instruction, and we're going to make sure that whatever's in EAX is 32-byte aligned. And remember, we've made sure that all branch targets are 32-byte aligned. So we know everywhere that we're going to be executing code, we've validated that those instructions are okay and can't be used to escape the inner sandbox. The NACL SDK also contains a standalone code validator. And I have an example of that up here. After you've compiled your NEXI module, you can just run this. So what I did was I took a hello world binary that comes with the SDK, and I modified it just to contain a basic x86 return instruction. And then I manually ran the code validator on it. And you can see that it's loading each one of the ELF segments, checking their sizes and whatnot. And then it sees, and then the validator picks up on the executable segment and starts disassembling instructions. And it comes across my return instruction. And obviously I've put that in bold red font. It says return instruction not allowed, illegal instruction. And then it's going to keep going through and try and load the various different ELF segments. But at the end, the result is this binary is not trusted. It contains an instruction that might allow this NEXI module to break out of the inner sandbox. So we're not going to run it. So you can just run this on your binaries without having to load them in Chrome just to see the various different instructions that are banned. And the inner sandbox. I keep saying the inner sandbox, but I haven't really explained how it's enforced. The inner sandbox is essential to the security module, the security that's created by Native Client. It sort of keeps untrusted NEXI modules from having complete arbitrary access to the service runtime memory. And the service runtime is a trusted component. On x86, it's actually really simple and it's done really well. It uses the memory segmentation module. It uses various segment registers to keep code constrained within a certain area of memory. And I'm not going to go into depth on x64 and ARM, but really quickly, on x64, all move and branch instructions are subject to alignment, and there's guard pages to keep writes from happening where they shouldn't be happening. And on ARM, it's very similar. I'm not convinced of the security of the inner sandbox on ARM and x64 yet, but the x86 model is pretty well vetted at this point. And of course, when we transfer between untrusted and trusted code, we need to store states, right? We need to store register states, and those are all going to be stored in trusted TLS segments that are stored in this trusted service runtime memory. So on x86, we're going to use various different segment registers to sort of keep untrusted code in check and keep it within a segment of memory that we know will never be processed by trusted code. And we used familiar x86 segment registers for that. CS for code, DS for data, and GS for thread local storage, which is actually pretty similar to how operating systems do use them. Not all operating systems use them, but some do. And then of course, SS, ES, and FS are all set to the value of what DS is set to. When we need to switch between untrusted to trusted code, we need to use trusted instructions to do that. And that's done through two things. Springboards, which enable a context switch from trusted to untrusted, and we have trampolines, which enable a context switch from untrusted to trusted. And each of them is going to contain privileged instructions just by their very nature, right? In order to change those segment registers, we need trusted instructions to do it. So at runtime, these chunks of code get mapped in automatically by the service runtime. So you might be thinking, well, why can't I just return to those trusted instructions once my untrusted module is running? The reason you can't do that with the trusted springboard is because the very first instruction in the trusted springboard is a halt instruction. And that's because the trusted springboard is only meant to be executed from the service runtime. And you can only call code within the trusted springboard at a 32-byte aligned address. So no matter what you do, if you try and call the trusted springboard from untrusted code, you won't be able to. You'll hit that halt instruction and the process will stop. Because it's only meant to be invoked from the actual trusted service runtime code. The service runtime also enforces that no new memory allocations can be marked as executable at runtime. It also enforces that only validated code pages have executable permissions, right? There's only one segment of memory that can be executable, and that has to be a segment of memory that was validated by the instruction validator. So an exe module, like I mentioned earlier, it can't make normal syscalls. It has to go through the service runtime. And it does this through this thing called NACL syscalls, which goes through the trampoline and the springboard interfaces. And there's basic syscalls for things like mmap, munmap, stat exit, and then there's syscalls to do things like srpc and IMC and low-level protocol stuff. The service runtime sort of implements IMC, and IMC is like a very low-level protocol, and it uses two different syscalls to set those up: IMC make bound sock, and IMC socket pair. And these ride on top of operating system supplied interfaces like Unix sockets and named pipes and shared memory. It just depends on the platform which one it's going to use. It doesn't really matter to you as an exe module developer. It does matter to you as an exploit developer. And of course, IMC is way too low level to be used by a native client module author. So there's srpc, which rides on top of IMC. srpc is a little bit higher level, a little higher layer than IMC, and it's going to serialize all the data I mentioned earlier, like ppvars. srpc endpoints are invoked via a really simple method here. I have a little chunk of code right here that says NACL srpc invoked by signature. And the first parameter you pass it is the srpc channel you're communicating on, and then just a string that describes the interface you want to call and the two arguments that you want to pass it and their types. And again, although srpc is a higher level than IMC, it's not meant to be invoked directly. So before I get into attack surface stuff, I just want to mention portable NACL, which is sort of like where native client is going but isn't quite there yet. And this is where native client will be found on ARM. So basically what the plan for Pinnacle is that it will have an LLVM runtime, and it'll take down an intermediate representation off the internet instead of an exe module. And it'll use LLVM's ahead of time compiler and turn that into an exe module containing native ARM code. The inner sandbox will remain the same, the Pepper proxy will remain the same, but it will bring 32-bit ARM support. I do think you can go download a dev release of that now. Okay, so this brings me to the part of the talk that I think people are actually here for, except for the people that are leaving. So native client, I have this golden rule up here, and I'm just going to read it verbatim. If a NACL module can execute instructions that were not validated by the service runtime, then the security provided by native client is broken. This is absolutely always the case. That's why the instruction validator is so strict. If any instructions get executed that don't match those rules, it's broken. You know, anything is game. On Chrome, outer sandbox escapes, they require a certain number of prerequisites. One is like vulnerabilities in the broker process, right? Of course, you can escape the outer sandbox then because you found vulnerabilities in a privileged component. And then there's like no or weakly sandbox components like the GPU process or like a plugin like the old Flash plugin was in Chrome. And then there's kernel vulnerabilities, things that the sandbox can't actually protect against at all, right? These are the things you need to be able to break out of the Chrome outer sandbox. But we can't really go after those things as an untrusted exe module. And that's because we're inside the inner sandbox. And the inner sandbox, as I've shown, has a lot of restrictions around the different things that you can do. You can't actually talk directly to the broker process. You can't make direct sys calls to the kernel. And there's instruction validations. You can't just break out of the inner sandbox by changing a segment register. So we have to sort of go after the things that are native client specific if we want to break out of the security that native client provides. Native client definitely raises the bar for exploitation in this regard. But again, you need trusted components to be able to do anything useful. And those trusted components are where we're going to find useful attack surface to go after. Just like I said earlier, vulnerable exe modules aren't an issue, right? Like, why would you exploit a vulnerability in a native client module and an exe module when you can just run your own exe module? There's really no point, right? And it does validation of like registers and everything, and make sure that even if you could exploit a use after free and an exe module, it wouldn't matter because you'd only be able to return to trusted code. So what we need to do is take an exe module and find vulnerabilities in the Chrome renderer and then go after them with that exe module. There's a few different things that we can go after. Of course, the inner sandbox, the ELF loader. ELF is notoriously hard to parse. the instruction validator disassembler, the NACL syscall implementations we can always go after. Things, they do low-level things like IMC, right? We always hear about syscall implementation vulnerabilities in like the Linux kernel, right? There's at least a few a year. The NACL syscalls are no different, right? They take untrusted data from the untrusted side and they process it in trusted memory. So this is all different attack surface we find in the inner sandbox. I don't believe anyone has found a vulnerability in the secure L floater yet, and I think that's because Google has fuzzed the crap out of it. Then, of course, there's the Native Client PPAPI plugin itself, which implements things like IMC and SRPC, two very low-level protocols, right? There's going to be low-level binary packet parsing code there. So that's definitely worthwhile attack surface. Then there's the JavaScript DOM interfaces. That's light, like I mentioned earlier, but of course it's still considered attack surface, as small as it may be. There's the JSON parser that's found in the Native Client plugin. There's the Pepper proxy interfaces, both server and client. They're reached via untrusted code. There's the GPU. If anyone's familiar with the Ponium contest that happened earlier this year, there's a guy named Pinkie Pie who exploited an integer overflow in the GPU process, and that integer overflow was reached via an untrusted NXE module, because NXE modules have sort of a lower level access to GPU command buffers than you would get via JavaScript. So I want to talk about some of the vulnerabilities that were actually found in Native Client so far. The very first one was found by a friend of mine, Alex Rad. And this was really early. This was in 2008 when Native Client was just still a research project. And of course, we're familiar with this code pattern up here. We're just doing this AND operation on the value of this register, and we make sure that whatever's in EDX is properly 32-byte aligned. The problem is that this call instruction actually calls what that address in EDX references. Right, so this is a really simple sandbox breakout. But again, this was back when Native Client was very much still a research project. Then there was the 2009 Native Client Security Contest that was held by Google. It didn't really, nothing came out of it that significantly really broke the inner sandbox design and said that this thing just isn't going to fly at all. They're mostly implementation bugs that could just be fixed, by changing a few lines of C++. I participated in the contest. I got beat very, very badly by Mark Dowd and Ben Hawks, two very, very talented guys. But I did come in second place with two colleagues of mine. And there were a bunch of other good entries. Some of these vulnerabilities don't really matter anymore, right? Because the architecture's changed so much since 2009. But some of them are still relevant to Native Client, and we can learn something from them. Some of my favorite ones was the eFlags direction flag modification. On 32-bit Intel, you have this status register called eFlags, and there's a bit in there that's like a direction flag, which is going to determine which way in memory data is written. And untrusted code could flip that bit and then call a NACL syscall and just automatically trigger a buffer overflow. That was a really cool vulnerability. And then I think Mark Dowd found an excellent vulnerability where you could just unmap validated code and map in unvalidated code. That was pretty embarrassing for Native Client, but obviously that's been fixed. It was a vulnerability I found, an uninitialized vtable. A lot of Native Clients implemented in C, and when I found that when Google writes C, they write it like it's C++. So they have all these manual vtables that they pass around with these structures, and they say, whenever you're using this structure, call functions from this vtable instead of whatever the regular fopen is. Call the fopen found in this vtable. And through an integer overflow, resulted in some uninitialized vtable and arbitrary code execution. Another one was this double delete operator, which was found in the NPAPI runtime. This was sort of confusion between who was responsible for freeing the C++ object. Was it the NPAPI backend code or was it the Native Client code? And although Native Client no longer uses NPAPI, you can still find the same types of issues with PPAPI. So yeah, even though the architecture's changed significantly since 2009, NPAPI is gone and Pepper's replaced it. The 2009 security contest really provided a good look at the future of Native Client vulnerabilities. There probably weren't going to be that many inner sandbox breakouts. It was probably going to be more vulnerabilities in stuff like the Pepper proxy that handle untrusted data. And that's very much held true to this day. Google themselves have found some pretty cool vulnerabilities in Native Client, and they've published them. One of the cool ones here on Win64 was this, when an exception happened, this function would get triggered, user exception dispatcher. The problem is that this function would get triggered in NTDLL, and NTDLL wasn't aware of the untrusted stack and the untrusted address space. So it would end up just trashing memory, trusted memory, whenever an exception was triggered. There was a few minor ones like this trampoline address space leak. A NextC module could read the untrusted trampoline code in memory and pull out a trusted address and know where things were mapped in the trusted address space. Some minor stuff like address space leaks via JavaScript. And then this brings me to, I'm almost running low on time here, but a source code audit that I did for Google last June. They were nice enough to let me talk about it. I audited the Pepper proxy. I guess they're done. It was just me for 3 weeks staring at C++ code. And it was just a manual source code audit. And I found 10 unique security vulnerabilities. A lot of them were around unserializing untrusted data. One of the cool ones I found was this PPB URL loader open, which basically used CORS, and CORS is cross-origin resource sharing. Anytime one website wants to make a request to another site, via JavaScript in your browser, it needs to make this request. And because this was, because this interface is called through C++, you could just inject an arbitrary carriage return and line feed and inject some random headers. Another cool vulnerability that I found was this PPB audio create use after free. And this goes back to that really complex glue code that sort of binds the Pepper proxy and SRPC. I found that what you could do is trigger like the audio interface again, for example, to fill up some buffer and then trigger a callback when it was done. But while it was busy doing whatever it was doing, the NextC module would invalidate that SRPC channel. And then when the Pepper implementation was done, it would go to then call the stale SRPC channel pointer, and you'd get an exploitable use after free. And the proof of concept for this bug was great. I just added like a call to exit after I called that function, and it instantly sad tabbed Chrome. A lot of other run-of-the-mill vulnerabilities, integer overflows that led to memory corruption of different sorts in shared memory. One, I believe, was shared memory with a broker process. Never really investigated that much, but I think that could have been a sandbox escape. All in all, a bunch of cool vulnerabilities that led to heap overflows and information leaks, various different exploitable conditions, all found through a source code audit. Length calculations turned out to be really difficult in the Pepper proxy due to all the serialized data. A lot of it's been fixed now. A lot of confusion over whether the Pepper proxy was responsible for validating a length variable or whether the PPAPI implementation was responsible for validating it. And then moving on, Google actually hired me and Matasano. I did a joint project with Matasano this past January to develop a fuzzer for the Pepper proxy. And this was a cool project I did with Cody Brocious, who spoke last night, actually. And Google deployed this fuzzer on their fuzzing farm, and I believe they're going to make this code open after Black Hat. It was very simple. It was just a NextC module that I wrote in C++. It had a bunch of various different utility functions for generating random data and calling lots of different interfaces, just setting up basic native client NextC module stuff. And then we had a bunch of Python scripts that took in these IDL files from the Chrome web source and these Python libraries that the Chrome developers wrote that sort of created an abstract syntax tree from those IDLs. And we basically just spit out C++ code into the NextC module template to automatically fuzz native client. So all you do is you just basically move this fuzzer into the new SDK version, do python generate.py, and you have an instant fuzzer for all the new interfaces that were added since the last version of the SDK. It turns out there's a lot of problems trying to fuzz from a native client module. One, you can't log to disk because the only way to log to disk is to call interfaces that you're currently fuzzing, right? You can't just open up a file because you're in a very strict sandbox. Another one was you need a constant source of random data. You can't just open dev view random if you're running on Linux. So we basically cheated there and made a call to JavaScript. And in Chrome, you can call like window.crypto.genRandom and get a bunch of random bits. We do that as much as we can, but again, that goes over an interface and the proxy that we're currently fuzzing. So we had some hard challenges there where we ended up just dumping log data to std out and just parsing it with various different scripts. So the exploitation of NACL is is kind of difficult. There's a few different scenarios you can imagine. Even if you got arbitrary code execution in the outer sandbox, you're still in the outer sandbox. Sure, you've defeated the inner sandbox, but now you're still in another sandbox. It's not equivalent to a WebKit or V8 bug. I've seen people talk about this on Twitter saying that, well, what does a Nexi module give me? I could just get a WebKit bug and exploit that. Yeah, that's true, but a Nexi module gives you access to lots and lots of interfaces that you simply can't reach from JavaScript. So there's a lot more attack surface because of it. So sort of conclusion slide here. Native Client's trying to solve a very difficult problem. The next time you hear anyone comparing it to NPAPI or ActiveX, just yell at them, because it's not even close to the same thing. Native Client's research into software fault isolation and sandboxing is absolutely going to influence sandboxes going forward. I wouldn't be surprised if 2-3 years from now, sandboxes that are out there have bits and pieces of Native Client's inner sandbox in them. I wouldn't be surprised to see this on Android in the next few years. It's sort of like a crazy idea, but I would love to see the Dalvik VM scrapped for the inner sandbox that's provided by Native Client, and I think it would greatly improve Android's security posture. And of course, for the paranoid among us, I always recommend that you run you run Chrome's click-to-play for all plugins, including Native Client. So that's the end. Does anyone have any questions? Questions? Use the microphone, I guess. Yep.
Hi, I saw earlier in your presentation that you had these list of trusted and untrusted modules. What are you attributing to the trust? What are you applying to the trusted modules? Why do you trust them?
So it all depends on what sandbox they run in, right? So two components that run in the inner sandbox, anything in the outer sandbox is considered trusted, because to be able to execute code in the outer sandbox, you basically need to elevate your privileges, right? Because the inner sandbox untrusted code is within the inner sandbox. So it really just depends on the context that you're looking at.
Sure, but why are you trusting the broker? Are they doing IV on the code, like integrity verification, or what are they doing to trust that code?
So the reason that the Chrome broker process is trusted is because you can't directly interact with it, right? JavaScript can only directly interact with the Chrome renderer process. And anytime it needs to access a privileged resource, it's going to go out of channel to the broker process and ask it to do it on its behalf. So it's just sort of like a separation of privileges there. I mean, that's just like Google Chrome's model. Right?
Okay, so if the binary was modified, it probably would know, right? If the broker is modified, it probably just run modified, right?
Sure.
Okay, good, thanks.
Yep.
So you mentioned the GPU-related thing during the sandboxing. So my question is, what's your thinking for GPU security, and is it possible we can sandbox the GPU code? Thanks.
I believe the question was, is it possible if you can like sandbox the GPU code and the GPU bug I brought up? I'm not a GPU expert, but it has to talk directly to drivers, to like graphics drivers. So I think that's why the GPU process runs with elevated privileges. I would really just refer you to the Chrome documentation on the GPU process. I'm really not an expert in that space, but I imagine that's why it has elevated privileges.
Do the two sides of the inner sandbox share a malloc?
So no, they don't share a malloc, right? The untrusted code has its own like libc in untrusted memory. And that sort of just gets shipped with the SDK and validated as well as the Nexi module. So if you were to call malloc, the untrusted module has its own stack, its own heap, its own everything. Is that it? Okay, well, thank you for coming to my talk.